Okay, so we started assorted combinatorial techniques. So first technique we exhibited is principle of inclusion exclusion, and there is this famous example of counting derangements, right? In how many ways, how many permutations are there which see each permutation moves each element. Any questions till now? Okay, so the next technique that we will do is the pigeonhole principle, also called the averaging principle. So we'll call it in short PHP. So this also you have seen many times, JE or before. So this states that if there are n plus 1 pigeons, and n pigeonholes, right, then what can you say about the number of pigeons in some pigeonhole? Right, so PHP says that at least one pigeonhole will have 2 pigeons. Then there exists a pigeonhole with greater than 1 pigeons. So at least 2 or more. Right, this is a trivial thing to prove. So what is the proof? How do you start? Yeah, no, that is the intuitive description, but formally you put say that A1 to AN are the counts of pigeons in these respective n pigeonholes. So let A1 AN be the sizes of the pigeonholes. So the key thing that we have done is we have sorted it, and so now what you can say is that since A1 is the largest, it has to be at least the average. Why is that? How do you prove that the maximum is at least the average? Yeah, you can just solve this inequality. You multiply on the left side by n, and then you see that left side you have A1s and RHS, you have AIs. A1 is at least each AI, right? So this is also trivial. Just follows from the inequality by scaling it up and comparing. And what is this now? So what is the sum of AIs? That is given to be n plus 1, which is then greater than 1. So how do you deduce that there are at least 2 pigeons in one hole? Yeah, so this is another thing, you know that AIs are integers. So since A1 has to be a natural number, this implies that A1 is at least 2. Is this clear? So what we assumed is that you don't kill the pigeons to death and part them in 3 ways or 4 ways, right? That's a humanitarian thing to assume. And so AIs are all natural numbers, and you get A1 at least 2. So this is also the averaging principle. But for some reason we call it PHP. Okay, so what are the immediate examples of this? So suppose there are 367 people. Right, so what can you say about the number of people that share birthdays? Yeah, so there will be at least 2 people who will have the same birth date. Yeah, or birthday actually, not the date. So there exist greater than equal to 2 people with the same birthday. So in these examples, you basically have to identify what are the pigeons and what are the pigeonholes, so that you can just apply the PHP theorem, right? So in this case, what are these abstract pigeons? That's so the people 367 are the pigeons, right? You abstract that out, and then the days are the pigeonholes. And in every day, multiple people can fall. The point is that a person cannot have 2 days, right? So because of this asymmetry, you associate people with pigeons and days with the pigeonholes. So people while the days are the pigeonholes. So that is all you have to do. You just have to set up the correct association, and then you can deduce these repetitions using PHP. But this will soon get quite complicated. Okay, this how to do this in a general problem, it will not be clear. So let's gradually take harder examples. So let's say Facebook has n users. Right, and it means that these users, user 1 and user 2 may be friends or they may not be friends, right? And one person may have many friends and so on. And friendship is obviously a symmetric relationship also. So we assume those things, and then you deduce that there exists at least 2 people who have the same number of friends. Okay, so now this will not be a direct application of PHP. There will be one more step in the middle. So first of all, how do you now associate pigeons and pigeonholes and try to do PHP? Yeah, so every person is you think of that as a pigeon, and the pigeonhole will be number of friends, right? The count. So So let's say users are u1, u2 dot dot un, and this every element here person will be mapped to some count. Now the count can be 0 or 1 or n minus 1, right? So that is the mapping of number of friends. So ui can be any value between 0 to n minus 1, but these are n values. So it seems that there are n pigeons and n pigeonholes. So how do you deduce that? How do you apply PHP? Right, so there will be one extra step here, which is you have to do a case study. So case 1 will be, you want to look at 0, or we can also look at we can look at either 0 or we can look at n minus 1. Let me see what I have. Yeah, let's start with 0. So there exists a UI with 0 friends. Okay, so if this person has 0 friends, in this case, is it possible to use PHP now? How? So now, let's say I is equal to 1 without loss of generality. So number of friends of u1 so u1 has no friends. You look at the other users now, u2 to un. What will be their counts? It can also be 0. So the thing is that if u2 to un anybody has again 0, then you are done. So let's maybe mention that here. If there exists an I greater than 1 such that the count for UI is again 0, then we are done, right? So with that side note, we can remove 0. So now we have only 1, 2 or n minus 2. Is that clear? We have deleted 2 elements from the image. Because, so we delete 0 because if there is some other, let's say u2 has 0 friends, then u1 and u2 have a match. And if none of these uj's have 0, then minimum will be 1, and maximum can only be n minus 2 because there are only n minus 1 users in the set, right? So now there are n minus 1 pigeons and n minus 2 holes, right? So this means that you can use PHP. There exists UI not equal to uj with the counts being equal. Okay, and that's, so this case is then also done. Is this clear? So is the proof over or is there anything else to do? What remains? Yeah, so case 2 still remains that 0 is not used in the original map at all, right? But then it will be like PHP because you have n pigeons and n minus 1 pigeonholes. So this is a more complicated application of PHP. It's used 2 times in different cases, disjoint cases. So now, what was the, it doesn't, for all UI, friends is positive. So when this happens, then U1 to UN is mapped to 1 to n minus 1. And so again by PHP, there exist different people, different users with the same number of friends. So that's again what you wanted to show. Any questions? Okay, so yeah, so let's move to even more complicated example where it will be not clear what are the pigeons and what are the pigeonholes. So this is about something we discussed in the overview of the course. What you have to show is that given a number n, you have to show that there exists a number m containing only 0, 1 digits and divisible by n. Okay, we write this, I think we used the notation before, we say n divides m like this. Okay, so for an arbitrarily given n, we have to show a number which is divisible, which is a multiple of n, but it has to be very special looking. It should just have zeros or ones in the digits. Okay, and this is not a binary representation, this is decimal representation. If it was binary, how will you prove it? Well, then it will be trivial, right? You can just pick m equal to n itself, and in binary it will have 0, 1. So we don't ask the trivial question. This has to be the decimal representation, all 0, 1s, divisible multiple of n. So what do you think are the pigeons now? Sorry? You will take sequence, oh yeah, all one sequence. So you have seen the proof before then. Okay. That's the only explanation. So let's consider so let me write it properly. This is the proof. So consider the pigeons as unary numbers which means that you look at 1, you look at 1, 1, Okay, look at this infinite sequence which are just unary, so which means that the only thing they are doing is multiple ones. Okay, so 1, 1, 2, 1, 3, 1, 4, 1 and so on. So these will be the pigeons. And what are the pigeonholes? Yeah, so pigeonholes will be when you look at these numbers mod n, or in other words, you divide these by n and look at the remainder. So remainder is thought of as an integer between 0 to n minus 1, right? So these are the pigeonholes. Okay, so this infinite sequence of unary numbers is mapped to the set, finite set 0, 1, n minus 1. But how do you apply PHP? Yeah, two of them should have the same remainder. Is that clear? So how many do you need in the orange set to apply? Only n plus 1 are needed, right? So as long as that set is n plus 1 or larger, you can apply PHP. Difference of or two unary have the same remainder. So there exists a remainder such that unary number 1 minus number 2 is divisible by r. Sorry, by n. Yeah, let me write r then. So u1 and u2 have remainder r. By n, divided by n. I use mod, I hope it's something you already know. But this mod is like r percent n, u1 percent n. Something that you see in the C programming. So this is just the percent operator. I call it mod operator or modulo operator. So u1 percent n or u1 divided by n and u2 divided by n both leave the same remainder, which is r. Okay, there will be such an r in the pigeonholes because the pigeons are too many. Now what do? You will take the difference. But will it have only 0 or 1s? Why is that? Right, so these are unary, so you pick the smaller one, subtract from the bigger one. So in those places, you will get 0. Right, so you will have a sequence of 1 and then a sequence of zeros, that's the answer. So it's far more special than you would imagine when the question was asked. You would try to place 0 and 1s in a random interleaved way, but you don't need that. Even if you just put sequence of 1s and sequence of zeros, still there is a number. Right, so it's much stronger than what was asked. So if you assume that u1 is greater than u2, then u1 minus u2 is basically 1 star 0 star. Right, it's a sequence of 1s and sequence of zeros. And obviously it is not 0 itself. U1 and u2 were different. Right, so it's a non-zero number which is in decimal representation, sequence of 1, sequence of zeros, and n divides u1 minus u2. So that is your m. that was asked. Is that clear? Any questions in this proof? So here finding the definition of pigeon is requires creativity, because the question doesn't say anything about how you will use these pigeons. If you started with some other kind of 1-0 sequences, it may get more complicated. But this simple thing works. Okay, another example that will be further complicated. So I will not do it. You have to do it in assignment 2. Yeah, you should also get an opportunity to solve questions, right? So what you have to show in one of the questions in the assignment is that if x is an irrational number, right? So basically, notation wise, it's like this: x is in reals, but it's not in rationals. Okay, so if x is outside Q and it's real, then what you have to show is there is a rational number, then P by Q exists, or let me say PQ integers exist. There exist integers P and Q such that it approximates x. And quite well. And I should have said for any n actually. And strictly less than. So what this complicated expression is saying is that for any irrational real number, you can get a rational approximation which is sufficiently close. Okay, so x minus p by q is smaller than 1 by nq. Now notice that it is for any n, so I should actually put an additional constraint here, and q has to be small. That's the full statement. So there will be for your given parameter n, there will be a small q such that denominator is small and p will adjust accordingly, such that x minus p by q will be quite close. It will be closer than 1 over nq. If you think of q as around n, then this is a 1 by n square approximation. Okay, so what this is saying is that although you have an irrational, you can still find a sequence of rationals which get closer and closer to x. Okay, but they will obviously never reach x, because if they reach x, then x will become rational. So without reaching x, they will always be approximating x with an increasing and arbitrary precision. So that's a rational approximation. So rational approximation of irrationals. And in fact, what you have to show is that this is if and only if. So converse also holds. Okay, so both the things you have to prove in that assignment problem. That if you started with an x that is outside Q, this P by Q will exist. And if this P by Q sequence exists, then x has to be outside Q. Is the statement clear? Right, and this, obviously this doesn't tell you anything about what are the pigeons and what are the pigeonholes. Right, so that silly theorem, you will not be able to fit here very easily. So you have to work harder and show this. So let me skip this. And yeah, let us change the PHP slightly. So by the same kind of proof of PHP, you can get an actual averaging theorem where the pigeons are more. So Rn plus 1 pigeons and n pigeonholes. So what can you say now as R increases? In theorem 1 it was R was 1, but suppose R is 100. Yeah, so then now you can say greater than R. So there exists a hole with greater than R pigeons. Right, and the proof is similar. So again you look at A1 greater than equal to A2 be the sizes, and A1 is the max, so A1 max is at least the average. The average is given to you, that's Rn plus 1 by n, right? So that's greater than R. So if you look at the max occupancy of pigeons, that will be R plus 1 or more. Is that clear? So that's the averaging principle, and let's apply it almost directly to again an example that you have seen I think before. So you have in a hexagon, so hexagon has 6 vertices, right? So how many edges you can draw? 6 choose 2, right? So you draw all the edges. There are these 6 choose 2 lines, and you color them. Red or blue. Okay, so there are these 6 choose 2 lines in a hexagon colored in 2 ways, let's say red and blue. And what you have to show is, it's a famous example, right? You have to show that there is a monochromatic triangle. There exists a monochromatic So this monochromatic triangle will be of what color? Red or blue? Both. No, but is it possible that we are trying to show that both of them are there? What is a counterexample? Yeah, if all you use was red color, then obviously you will never get blue, right? So what is meant here is that there will be a triangle which will be either all red or all blue. So one of these is guaranteed. How do you prove this? Using the averaging. So what are the pigeons? What are the pigeonholes? Focus on one vertex. So vertex 1 and the other vertices are V2, V3, V4. This may not be good. And so now, our focus is on V1, and the neighbors are 5 many. What can you say about the edges which connect V1 to these? Yeah, so you apply theorem 2. So there are these 5 edges which are the pigeons, and there are only 2 holes, like either red color or blue color. So 5 by 2 is more than 2, so there will be 3 of one type. So let's say these 3 are of one type, and let's call them either blue or red, so let's pick red. So focus on V1. There exist 3 edges of the same color. Say red. Okay, so here we are using theorem 2. Next what? Yeah, so we will actually ignore now V4 and V5 edges. Somehow they will not even appear in our argument. We'll only focus on the red edges. And so now you see this V2, V3, V6. That triangle, it has 3 pigeons, and again there are, as always, 2 pigeonholes, right? Which means that, actually, do I even need that? Yeah, okay. Yeah, so actually now there will be cases. Yeah, before applying theorem 2, you have to look at these 2 cases. So it's possible that the triangle is already monochromatic, right? Which is the bad option is blue. So suppose it's already blue monochromatic, then you are done. You have a blue triangle. The other case is that it's not, which means that there has to be a red edge. What happens then? Yes, so in that case, you get red triangle. So you now focus on these 3. Okay, and you argue on these 3 now, V2, V3, V6. So either it is blue colored, which means that you are done, or it is not, which means that there is a red edge. If there is a red edge, then let's say V2, V6 is red, then you will look at V1, V2, V6, that's a red triangle. We get a red triangle with V1. Is that clear? So, yeah, so we used the averaging principle only once here. Okay, and after that there were cases. That is how these combinatorial proofs will usually be. The complicated ones you have to break cleverly into cases, then do a case study. Somewhere you do averaging, somewhere you do something else. So in the assignment, there will be a more complicated version of this problem. By the way, can this be done with something smaller than hexagon? Do you need 6 points or is it also fine with 5 points? So in a pentagon, will you always find a monochromatic triangle? Yeah, so that you have to do as an exercise. Show that this, so that the proof is optimal or tight. That is, it's not true for pentagon. Okay, so in a pentagon, you will not find, you will be able to color in a way so that there is no monochromatic triangle, but in a hexagon, this is no more possible. No matter how you color, somehow a monochromatic triangle always appears. Right, so that's, it is something hard to guess. Right, you will not guess it in the first instance. And also, you don't immediately see the difference between 5 and 6. Now, if you have a heptagon, what happens? If there are 7 vertices? Right, so once this threshold is crossed, then it is always true. And if you are behind the threshold, then it's always false. Right, so why is this threshold 5 to 6? That you will not guess a priori. But once you see the proof, then you know it. Sorry? Okay, if you say so. Prove as an exercise. Yes, some sort of that thing will be there in the assignment. So this is the, so you have now seen 2 tricks. The pigeonhole principle with averaging, and before that you saw inclusion exclusion. Any questions till now? Because we will now switch to the third trick, which is more non-trivial than this stuff. So that will be combinatorics using linear algebra. So it seems that linear algebra hides a lot of combinatorial properties. Okay, and conversely, if you have a combinatorial question which has nothing to do with algebra, many a times, at least in the interesting cases, you can formulate or model it as an algebraic question, and you can even solve it by linear algebra using vector spaces. So that is what we will do now. Maybe we will not finish it today. So let's do it. So in many interesting combinatorial constructions, algebra plays a key role. It's a major tool. You may not have seen finite fields, etc. So when we do it in the end of the course, you will see more of this. And certainly in other courses, you will see that finite fields are used to construct a lot of combinatorial objects. But here we'll have low ambitions. We'll just focus on linear algebra without more complicated algebraic objects, but already it will be an illuminating example. So if you are more interested in this, then there is a whole book dedicated to this title, Linear Algebra Method in Combinatorics, by Babai and Frankel. So there is this book, and there is another book or many books which have this probabilistic methods in combinatorics. So linear algebra and probabilistic methods, these are two important ways to construct or at least show the existence of combinatorial properties. The probability part we have removed from this course, so that you do separately in the probability course, but questions are the same. Both these tools are very powerful and probably the only way to do serious combinatorics. So here the example will be suppose you want yeah, let's go with the example of clubs in a college. So what happens here is that there are n people in a college, and they want to form several clubs, and there will be constraints put on the way clubs are formed. So first of all, the club should be distinct, which means that two clubs should not have the exactly same members. Okay, so if you look at two clubs, then there should be at least one member which is absent in one, present in the other. Right? That's a natural constraint. And there will be one more complicated constraint. So let's start with the first possibility, which is there are n members. Each club should have even number of members. And the intersection of two clubs should also be even. Okay, so these are the three kind of axioms given to you to form clubs. So now, what is the maximum number of clubs you can form? What do you think is the estimate? Each club size should be even. Clubs should be distinct, and intersections should also be even. So instead of the exact count, what do you think is the ballpark estimate? Well, what simple thing is, you can just pair up people, form pairs, right? So form n by 2 pairs. If there were 100 members, you pair up first and second, third and fourth, fifth and sixth, and so on. So you will get 50 pairs. And then all possible subsets of these 50 pairs satisfies the constraints, right? So you get this immediate result that number of clubs that you can form is at least 2 raised to n by 2, and in fact it will be much more. Is that clear? Pair up the people. Sorry, NC2. Well, NC2 is only n square. I'm saying exponential in n. NC2 would just be. See, the club is a subset of members. Club is a subset of the college. So if college has n people, then subsets are 2 raised to n many, right? No, but I'm saying that the final answer is closer to 2 raised to n, not NC2. It is 2 raised to closer to 2 raised to n because you can arbitrarily just form pairs, and even with arbitrary pairs, you still have a lower bound of 2 raised to n by 2. So the count is somewhere between 2 raised to n by 2 and 2 raised to n. Is that clear? You get both sides something. I'm not saying how good this is, but the number of clubs is somewhere between 2 raised to n by 2 and 2 raised to n, right? So if n is 100, then this is between 2 raised to 50 and 2 raised to 100, right? The number of clubs is huge. Any questions? So once you understand this, I'll change it slightly with a drastic consequence. Let's now change the conditions to again, I mean, the number of people is n, that is fine, but the key conditions are each club size is odd. And the intersection of clubs is even. This remains even. Okay, so previously it was even, now it is odd even. Is the change clear? So what this does is that it kills this idea of pairing the people and considering all possible subsets. Right now you can't do that because odd seems to introduce a tough constraint. You have to make sure that the members you are picking, they are odd, right? You cannot get odd by just collecting many evens. So if you collect many evens, you also have to collect an odd. And if you collect odds, it should not be 2 odds, it should be 3 odds, right? So now more and more constraints get introduced into the system, becomes harder to analyze. So what is the answer of the question now? So what is the number of clubs? What do you think? Previously it was exponential, 2 raised to n by 2 or more actually. How much is it now? Any guesses? So you haven't seen this example then. This is a tough example. So for some weird reason now the number will be n. Okay, so if you put this changed constraint, then you will have very, very few clubs. From exponential, it will come down to linear. Okay, from 2 raised to 50, it now comes down to just 100. So why is this, why will this happen? So that explanation will be given by linear algebra, which well, we can start the reduction, finish it next time. Yeah, sure. I mean, we want to maximize the clubs. So we want to maximize this. It's a maximization problem. Yeah, sure. Up to these constraints. Any subset of the college is a club. So equivalently, you can just look at it as subsets of 1 to n. So it's a combinatorial object called set family. So we are looking at a set family where the elements are sets, and in the first type, all the sets have to be even, all the intersections even. In the second set family constraint, the family has the property that the sets are all odd, all intersections are even. Okay, and that changes things drastically. It's too much of a constraint to form the set family. So the way you will analyze this is, since I want to introduce linear algebra, maybe you should guess what will be the vectors. In terms of clubs, what are the vectors? What is the ambient space, ambient vector space? So the ambient vector space is the, let's say, q to the n. Or you can take r to the n, it will not matter anything. Okay, so it's the n-dimensional Euclidean space, and a club is basically a 0, 1 vector in the ambient space. It's a point in the vector space, which is what? It just indicates, right? Every coordinate will indicate whether the member is in the club or not. So a club is a point. Or actually point or vector in this space. So for example, if your club is the people or person 1, person 3, person 10, then it should be mapped to the point. So yeah, the first location in the vector is set to 1, second is set to 0, third is again set to 1. Then you have 4, 5, 6, 7, 8, 9, and then 1. And everything else is 0. Okay, so members in the club, they basically put the coordinate either 1 or 0, depending on if they are present. So every club you can see as a point in the ambient space. And now you have to analyze what do the constraints say about these vectors. Okay, based on that, we will get the number n. You can ask questions.